Welcome back to Metaphor Math, and we're on to 4C of Chapter 1 of Intro to Analysis by Rosenlicht. And in this problem, we are showing another set equality, and we're going to do this like we've done in past videos where we're going to show that the left-hand side set is a subset of the right-hand side set, and vice versa, that the right-hand side set is a subset of the left-hand side set. So let's get started here. So let's start by showing that for shorthand, I'm going to say left-hand side set is a subset of the right-hand side set. So let's take any x in this left-hand side set. So let's take any x in A minus B minus C. And if we can show that this general x that's in this left-hand side set must also be in the right-hand side sets, then since this x, the only property that this x has is that it's in this left-hand side set, and since all the x's in this left-hand side set have the property of being in A minus B minus C, then if we can show that this x must also be in the right-hand side set, then we've shown that all x in this left-hand side set must also be in the right-hand side set. So let x be in A minus B minus C. So if x is in A minus B minus C, then by this property right here, we can say that this implies that x is in A x is in A intersect B intersect the complement of B intersect the complement of C. And since x is in A intersect the complement of B intersect the complement of C, by the definition of set intersection, that means that x is in A and x is in the complement of B intersect the complement of C. And by the definition of the complement, that means that x is in A and x is not in B intersect C. Now, for any x in A and x that's not in B intersect the complement of C, we could have two possibilities. We could have that x be in B, or x is not in B. Now, if x is in B, then since x cannot be in B intersect the complement of C, then we must have that x is in the complement, x is not in the complement of C. So, for case 1, if x is in B, then this implies that x is not in the complement of C. That's because in order for x to not be in the intersection of two sets, then it must be such that x cannot be in at least one of the sets. So, if x is in B, then if x were also in the complement of C, then that means that x would be in B intersect the complement of C, which would contradict the fact that x is not in B intersect the complement of C. So, since x is in B, that means that x is not in the complement of C, which is the same as saying that x is in the complement of C. And we've proven this in a previous video where this set is the same as x is the same as C. This set right here is the same as C, so that means x is in C. So for case 1, x is in B and x is in C, but also, remember, x must always be in A, so this implies that x is in I skipped a step there. X is in A, and x is in B, and x is in C. Now, this is the same as saying, by the definition of set intersection, that x is in A, intersect B, intersect C. Now, for case 2, where x is not in B, then if x is not in B, then since x is not in one of these two sets here, x is not in B, so therefore it must not be in B intersect the complement of C. We've satisfied the property of x not being in B intersect the complement of C already by x not being in B. So, if x is not in B, then that implies that x is in the complement of B, and x is in A because x must also always be in A. by what we stated up here, but what we derived up here. And if x is not in B and x is in A, then that's the same as saying that x is in A intersect the complement of B. And by this property up here, right here, that means that that implies that x is in A minus B. And since either property 1 or property 2, or excuse me, since either possibility 1 or possibility 2 can hold, we have that x is in A intersect B intersect C, or x is in A minus B, which is the same as saying x is in A minus B union A intersect B intersect C. And we've done it. We've shown that a general x, any general x that's in this left-hand side set, A minus B minus C, must also be in A minus B union A intersect B intersect C. So let's do the same thing going the other direction, where we show that if we take any general x in A minus B, so let x be in A minus B union A intersect B intersect C, if we can show that any general x in this set right here, must also be in A minus B minus C, then we've done it. We've shown that the right-hand side set is a subset of the left-hand side set. So let's do that. So let x be in A minus B union A intersect B intersect C. So we have two possibilities here. Either 1, x is in A minus B, or 2, x is in A intersect B intersect C. So let's take possibility 1 here. I'm gonna give myself some more room here by marking this off so that we don't get confused. So if x is in A minus B, then that implies that x is in A and x, or excuse me, I skipped a step here. That implies that x is in A intersect the complement of B, which implies that x is in A and x is not in B, by definition of intersection and by definition of complements. So, if x is in A and x is not in B, we also know something else here. We know that if x is not in B, then it can't possibly be, then x is not in B intersect x for any set x. Because in order for x to be in B intersect x for any set x must both be in B and x. There's a lot of b's going around. So if x is not in B, then it can't possibly be in B intersecting any other set. So if we just put in, so that means that we put in the complement of C here, so that means x can't possibly be in B intersect the complement of C, and B intersect the complement of C is the same as saying B minus C, and that means that if x is not in B minus C, that means that x is in the complement of B minus C, and since x is also in A, that means that x is in A. So by the definition of set intersection, that means that x is in A intersect the complement of B minus C, which is the same as saying, by the definition of the differences of two sets, x is in A minus B minus C, like that. All right, and so let's take the second possibility here. Let me give myself some more room where x is in A intersect B intersect C. I'm going to go over here. Mark this off. Let me change colors just so we can know what we're talking about being different from everything else here. So if x is in A intersect B intersect C, then that implies by definition of set intersection that x is in A and x is in B and x is in C. Now, if x is in C, I'm going to kind of do the same thing that I did over here. Over here, I'm going to say, well, if x is in C, that means, this implies that x is not in the complement of C, because if x is in C, then it can't possibly be or excuse me, yeah, it can't possibly be in the complement of C since it's in C, since the complement of C is everything that is not in C, so it can't possibly not be in C, so it's not in the complement of C. So if it's not in the complement of C, that implies that X is not in X intersect the complement of C for any set X, for any set X, because in order, oh, I said set twice, excuse me, sorry about that, for any set X. Because, remember, in order for X to be in X intersect the complement of C, it must both be in the set X and the complement of C. But we've already said that X is not in the complement of C because X is in C. Because X is in A intersect B intersect C. So, if X is not in X intersect the complement of C for any set X, then that means for sure that X is not in B intersect the complement of C. And this is the same as saying by the definition of set difference that X is not in B minus C. And if X is not in the set B minus C, then X, by the definition of complement, X of set the complement of a set, X is in the complement of B minus C. But remember, we also have that X is in A. We also have that X is in A. So, and X is in A. And we can rewrite this as X is in A intersect the complement of B minus C, which implies that X is in A minus B minus C by the definition of the complement, or the difference of two sets. And we've done it. We've shown in both cases whether X is in A minus B, whether X is in A minus B. Let me zoom out here so we can kind of see everything here. We've shown that if X is in A minus B, then X must be in A minus B minus C. And we've shown that if X is in A intersect B intersect C, then X must also be in A minus B minus C. So in both cases, no matter what, if X is in this right-hand side set over here, then X must also be in this left-hand side set over here. And we've also already shown the other direction where if X is in the left-hand side set, it must also be in the right-hand side set. So, and this picture here, when you prove this on your own, and I would encourage you to not watch this video, try this problem and try to prove it without watching this video, and then watch this video to check yourself. Or if you get really stuck, if you get really stuck, then watch this video to kind of help you along. But this picture was helpful for me in solving this as well. Anyways, have a good one.